Okay, so this talk's going to be about how we can generalize a supervised CCG parser using unlabeled data. As is popular today, we're going to be doing that by using word embeddings and neural networks. While the techniques we're going to use are pretty standard, we're actually going to get some really big performance improvements both in and out of domain by using this. And perhaps what's more scientifically interesting is I'm going to try and give some error analysis to motivate these techniques and show where they gain over traditional features like past speech tags and lexical features. First of all, I'm going to quickly describe what supertagging is and why it's useful. So these are some CCG supertags for the sentence fruit flies like bananas. So these tags go beyond past speech tags by encoding information about predicate argument structure. So this category for like here says that it's not just it says it expects the noun phrase argument to the right and noun phrase argument to the left as a function of these into a sentence. So it's saying that like isn't just a verb, but it's specifically a transitive verb. The nice thing about supertags is that given the set of tags, then the parser can't really go wrong. From these tags, it's bound to get this interpretation of the sentence. Obviously, we can assign some different supertags to these words. Here, this tag for fly says that it's an intransitive verb because it wants one noun phrase to the left. And again, with these tags, then, we're pretty much guaranteed to get this interpretation of the sentence. Obviously, the converse also holds, so if we don't get these tags, then we can't possibly find this interpretation of the sentence with the parser. So supertags go beyond pos tags by encoding predicate argument structure, but the price you pay for this is that you need far more supertags than you need pos tags. So CCG Bank contains well over 1,000 supertags, but we normally use a set of 425. But it still causes a huge amount of sparsity and lexical ambiguity. To give an example of how ambiguous words can be in CCG, I mean, here's a bunch of sentences involving the verb fried. And what's interesting about all of these is they all use different supertags for fried. You can use different supertags depending on what types of arguments and how many arguments these words are taking. And obviously not all verbs will take all of these supertags, so say an intransitive verb like sneezed will take a very different set of tags to these. So what's interesting about this is we got like maybe 9 reasonable supertags for fried that I listed there, but the verb only occurs once in the whole Wall Street Journal, training data anyway, so it's very unlikely that we're actually going to learn a good distribution over these 9 categories in this. Next, I'm going to describe an existing CCG parsing model and explain how that uses supertagging. So we'll describe the CNC parsing model from Clark and Curran. What they do is they try and generalize based on past speech tags. So first of all, they pos tag a sentence, and then they use their pos tags and lexical features to try and predict a distribution over supertags for each word. And they use these features for all the words in the local context window. So supertagging is about 90% accurate, and to get the right parse, you really need to have the right supertags. So that's nothing like accurate enough. They try and get around this by what they call multi-tagging, which is outputting a set of tags for every word. The way this works, first of all, you supertag with a narrow beam where you output on average 1.3-ish tags per word. So for example, here fruit's got both a noun and an adjective category. And then you try and parse with these supertags. If you have these supertags, what you'll find is that you can't actually build a complete parser sentence because you've got both flies and like being verbs with these categories. So what they do then is they go back to the supertagger and they retag the sentence with a broader beam, so they're allowing more tags per word. And if you do that, you can get one interpretation of the sentence using the supertags I've highlighted here, and another interpretation using these supertags. And in general, you'll have lots of different parsers for the sentence with a set of supertags. they get all these parsers and they rank them in a big log linear model with lots of features, the dependencies and derivation. Okay, so just to summarize so far, I've argued that accurate supertagging is essential for accurate CG parsing, and that I've described an existing model which uses pos tags and lexical features, and multi-tagging to mitigate errors. Next, I'm going to just do some error analysis of this parser to try and see how it can be improved. This graph shows the performance of the CNC parser. On the left, we got it on CCG Bank, which is a Wall Street Journal text, and it gets around 85% accuracy, which is basically state-of-the-art for CCG parsing. CCG parsing uses a much harsher metric than most other parsing evaluations, which is why the state-of-the-art is around 85. Then when we switch to Wikipedia text, we find the accuracy drops off by around 5%, which is obviously quite bad. And then when we go to biomedical text, it's performing around 10% worse than it is on the Wall Street Journal. So clearly the parser is not generalizing well to out-of-domain text. I'm going to try and I'm going to suggest that the supertagger is partly to blame for this. Okay, so I'm going to show a few curves like this in the stock. These curves show the performance of the supertagger. On the x-axis, what we're doing is increasing the number of average tags per word across the corpus. So this is showing the effect of increasing the supertagger's beam width, as it's done during parsing. The left end shows the initial beam used by the parser, where parsing is very fast, and the right end shows the final beam it uses, where parsing is very slow. And if it doesn't find the right, if it can't find a parse by then, it just gives up and fails. You can see that on CCG Bank in domain, it's going from around 97 to 99%, which seems fine. But when you go out of domain, the error rate is basically doubling, so it's only doing around 94% with a tight beam and a little over 97 with a relaxed beam. So the supertagger is getting a lot worse out of domain. Next up, I'm going to suggest a few reasons why that might be the case to try and motivate a new model for supertagging. The most obvious reason why it might get worse out of domain is that it's got a lot of unseen words and new vocabulary it doesn't know how to tag. It turns out that there are loads of really frequent words which don't actually occur in the Wall Street Journal, for example, 10. And it's hard for the supertagger to get these right. This curve shows how the supertagger does on these, and you can see that it drops off by a good few points on specifically unseen words compared to ones it has seen before. But it's still reasonably accurate, partly because most unseen words are probably just nouns. There's also a slightly more subtle case, which I'll call unseen usages. These are words that do occur in the training data for the parser, but they occur with a different category to the category you need in test data. So I mentioned that Freud might have 9 good categories that you might see in your test data, but you only see it once in your training data with one of these. An example I like is that the word European occurs a lot of times in the Wall Street Journal as an adjective, as in European minister, but it never ends up occurring as a noun. This is just a fluke because American does occur as a noun. But the trouble is that this convinces the parser so much that European must be an adjective that actually completely fails to parse the sentence, every European is a person. So it's a bit worrying that a state-of-the-art parser these days can't parse a sentence as simple as that. On these words, the performance drops off dramatically. I've changed the scale here, but it's gone from around 97% accurate to barely over 50% on these with a tight beam. So clearly the supertagger is really struggling with these words, and they're going to have a big impact on performance. Another obvious source of errors with this model is pipeline errors. Because we're using a pos tagging first, while pos tagging is reasonably accurate in domain, then it gets a lot less accurate when you go out of domain. For example, it drops to 93% on biomedical text, and obviously the supertagger thinks it's going to be talking to a 97% accurate pos tagger, and it's going to trust it far more than it really should. And in the green line here, I show the performance on these things, and we can see that it's only around 70% accurate, and even with a very wide beam, it's still not even 80% accurate. So to summarize so far, these traditional part-of-speech tags and lexical features are actually quite brittle, and they're vulnerable to cases such as unseen words, unseen usages of words you have seen, and pos tagging errors. And these errors problems all get a lot worse out of domain, contributing to quite weak out of domain performance. Okay, and a more general summary would be that 1 million words of Wall Street Journal is nothing like enough to learn a good supertagging model. Okay, so this motivates the idea of doing semi-supervised learning. There's been a bunch of recent models for this, but I think in general it's fair to say that they found it quite hard to make improvements. There've been improvements on special cases like unseen verbs and things, but generally state-of-the-art parsers are still fully supervised. So we're going to try and get around this using word embeddings. As I'm sure everyone knows, word embeddings are vector space representations for words, and you can pre-train these in an unsupervised way, for example, using neural network language models. So what we might find is that we've got similar words close together in our vector space. So fried is near baked and cooked, and European is near American. So there's been a lot of work using embeddings as features and classifiers, and it's worked very well on a lot of tagging tasks, for example, part-of-speech tagging, name identity recognition, and chunking. There are also some good results in dependency parsing coming very recently, but it's proved a lot harder to do constituency parsing with these kinds of models. It's kind of less obvious how you can use them as features in these. For example, there's a very nice paper by Jacob Andreas at ACL this year, where he tries a whole bunch of ways of using word embeddings as features in the Berkeley parser, and basically it's a negative result. He couldn't find anything that would make the parser work better using embeddings features. Okay, so it's kind of two open questions. Firstly, how we generalize CCG parsers using unlabeled data, and secondly, how we can improve constituency-type parsing approaches using word embeddings. And as you probably guessed, the solution I'm going to propose is using embeddings as features in the supertagger, which kind of lets us reduce parsing to a tagging task, which word embeddings are very easy to apply to. So we're going to assume that words that are close together in vector space are going to have similar supertags. So that will hopefully let us generalize from tags we've seen for words to similar words. So we're going to do this with a neural network model. The top layer is going to be a lookup table where we're looking at the embeddings of the word. And then it's basically a log linear layer on top. I've set this up as a neural network because that lets us backpropagate errors into the embeddings, so we can fine-tune the embeddings during the supervised training. And yeah, we're also going to use a couple of very general features using two-character suffixes and capitalization, which we hope will generalize well to new domains. So I think this approach has got a bunch of advantages over traditional features. Firstly, it completely avoids pipeline errors because we're not using a part-of-speech tagger. Because we can pre-train our vectors on a large unlabeled corpus, we've got far fewer unseen words. And we can also sort of share observations between similar words. So we're not really classifying words in this, we're classifying regions of the vector space. So we might be able to learn good categories for fried just by seeing the categories for baked and cooked and boiled. Okay, next up, let's see how this works on supertagging. So this is quite a simple model. There's not very many knobs we can tune to improve the performance. One thing I tried was varying the embeddings we were using. I downloaded a bunch of ones which are publicly available. Most of them work at a fairly similar level. So neural network language model works as well as anything else. Some of the ones that didn't work so well were trained on broadcast news, which might explain that. Or it's possible they're capturing semantic properties rather than syntactic properties. I also experimented with the size of the context window, and 7 words work better than 5 in general. Unfortunately, this is the performance of the CNC parser, Supertagger, which actually turns out to be better than any of our embeddings approaches, which was disappointing after all this motivation for this. I tried a bunch of things to try and get these models better, such as using sequence models where you condition on the previous supertag, and using hidden layers of various sizes and different neural network architectures. And basically none of these actually improved it very much, and I couldn't beat the CNC supertagger's accuracy. I almost gave up on this at this point, but then I tried using the supertagger in the parser, and something really interesting happens, where actually the parser performance improves quite a lot. So on CCG Bank, we get around 0.8% improvement, which is quite a lot for using semi-supervised methods with a state-of-the-art parser. And on Wikipedia and biomedical text, we actually get much bigger improvements of several points. So this begs the question of why the one best supertagging is getting worse, but the parser is getting better using the supertagger. This kind of curve shows the answer, really. So with just one tag if you're only outputting one tag per word, so the one best accuracy is actually lower than the CNC. But as you increase the number of tags per word, as is used by the parser, then the embeddings-based approach works a lot better than the traditional parser-speech tag and lexical features. I think the reason for this is that pos tags and lexical features are normally quite good on the easy cases, but because they're binary features, they're quite brittle. Whereas these real-valued embedding features are kind of more robust and can generalize better on the difficult cases. And you get a similar story on Wikipedia and biomedical text, where generally at all levels of accuracy, the embeddings-based approach works better. So I was also interested in the effect of adding other features to this model and to see does anything help the embeddings. So the blue here is the CNC parser performance. The first thing I tried was swapping out the embeddings for brown clusters. These brown clusters were trained on the same corpus as the embedding, so it's a fair comparison. And what we can find is that the brown clusters are slightly worse than CNC in domain, slightly better out of domain, but they work a lot less well than using embeddings, perhaps because they're these brittle binary features. I also tried adding parser speech tags to the embeddings approach, and the performance gets worse. That's presumably due to pipeline errors, and also suggests that the parser tags aren't really telling you anything that isn't already there in the embedding space. Also tried adding lexical features, and they basically made no difference. So again, it seems like the embeddings features are basically all you need for learning a good supertagging model. Next, I just want to try and show some cases where the embeddings are doing better than the traditional feature sets. So firstly, this is the accuracy on unseen words. You can see we get quite a big improvement of using the embeddings over the traditional features, presumably because we've got a much smaller unseen vocabulary with these pre-trained embeddings. There are far fewer out-of-vocabulary items. Next up, these are the unseen usages. So the CNC parser is around 50% on these, but using the embeddings improves that by about 20%. So we get a really big jump in performance on these cases where we've seen the word before, but not with the right category. Finally, these cases where the parser speech tagger has made a mistake. And again, we get around pretty much 20 points improvement on these. It's perhaps slightly surprising that performance of this model is still quite low, even though it's not using a parser speech tagger. But I guess this means that the performance of the embeddings drops a lot in these cases, even though we're not using a parser speech tagger, so it can't have pipeline errors. But I guess that means that whatever is making it hard for the pos tagger is also making it hard for the super tagger. Finally, did some comparison on different kinds of words. So in general, using the embeddings is working better on verbs and WH words, but less well on nouns and prepositions. I think this suggests that the cases where it's working well are ones where the words tend to be highly lexically ambiguous. So both verbs and function words in CCG kind of have very large sets of categories, and the embedding seems to be dealing a lot better with these. With the prepositions, the errors you make in these are generally making subtle distinctions between arguments and adjuncts. And yeah, I think these distinctions are often quite arbitrary, and it's possible this information just isn't there in the embedding space. Okay, so there's been a bit of debate in the literature about how much embeddings really do encode about syntax. And I think based on these results, we can say that the embeddings are really helpful for this. And we can use the embeddings, if we use embeddings for supertagging, that really helps with reducing sparsity and eliminating pipeline errors. And it all works particularly well out of domain. The code's released as part of my parser, which I'll be describing in the next talk. Thank you.
Hi. So it seems like what you really want out of your embeddings is functional similarities rather than semantic similarities. Sure. So I was wondering, so you only tried 5 and 7, and so word context, yep. And I think I've seen studies showing that, you know, even smaller context windows give you much more functional type similarity in the embeddings, like 3 or even 2. And then also, I don't know if you, I think Yoav Goldberg and Omer Levy had a paper about like dependency-based embeddings, and they got much more functional similarities that way.
Yeah, that's a good point. I saw that paper after I did this work, and I'd very much like to try their embeddings because I think they're capturing exactly the kind of information we need for this. So, yeah, it may get better if we slot those in, but I haven't tried that yet.
Do you have more questions? Well, I've got a question for you. I was just wondering, so I think you're learning something perhaps that's complementary in the Supertagger to what's in the parser. And I was wondering, are you actually retraining the parser as part of this setup? And if not, is maybe some of your gains coming about from the fact that you're getting some kind of ensemble voting between these two sources of information?
Yeah, that's a good question. I'm not retraining the parser, I'm just using the parser trained on the other supertagging model. Yeah, you get quite complex interactions between the parser and the supertagger, which do provide complementary information. And yeah, doing some kind of joint model would probably work better. So the best CCG parsing results are from Michael Lowley, who does exactly this. And I think if we slotted the supertagger into his model, then you'd expect to see further gains.
Sure. Are there other questions? All the way at the back.
Just a suggestion, but given your issues with out-of-vocabulary words, yep. Have you considered using morphologically compositional approaches for deriving the embeddings? So rather than just taking words as atomic, actually doing a decomposition?
I haven't tried that, no. That makes a lot of sense to try that, and you'd expect that would work better. Yeah, I mean, both morphology and the lemma should independently both be quite useful for the supertagging task. So yeah, I think these compositional approaches are very worth trying for this, but I haven't done that yet.
Do you have unseen tags at all?
Unseen tags? We do, yes, but we just can't assign those. So there's over 1,000 tags in CCGBank, but we just use a reduced set of 425, and anything that needs another tag we get wrong.
Okay. And this reduced set, was that something that CNC did already, or is that?
Yeah, I'm using the same set as I do. It's just a frequency cutoff they did.
Okay, right. Thank you.
Any more questions? I've got one for you. So the CNC Supertagger, I think, was a CRF, if I understand rightly. Did you consider a CRF objective in training your embedding-based model?
Yeah, I've got a result from that in the paper. It makes a very small improvement at supertagging accuracy, but it's also really slow because you've got this huge transition matrix you need to use for decoding, and it just wasn't worth it for parsing practically.
Great. Okay.
Your biggest improvement in supertagging accuracy was on WH words, and of course you've already seen those, I'm sure. Yeah. So is the difference that in the other domains they have different usages, or is it just they tend to occur in sentences that are harder to tag the supertag correctly because of other words that are in the sentence, or what's going on? Why are those the hard ones?
In CCG, these WH words can have really huge sets of categories, so and weird constructions like Pied piping and things, then you get these crazy categories for WH words. And I think you may not have actually seen all the word category combinations you need, so maybe you've seen the tag for which, but you haven't seen it for who or something. And I guess this approach is helping generalize in those kinds of cases. Mm-hmm. But yeah, I was surprised to get quite such big gains from those.
Okay, there might be room for one more question if there is one. Okay, otherwise let's just thank the speaker and let him get ready for his next talk. just moved along a slide. Okay, our next speaker is the same speaker. A-star CCG parsing with a super tag factored model.
Okay, so following off the last talk, in this talk I'm going to argue that the supertagger we learned in the previous talk is actually the entire model you need for a pretty good parser. I'm going to introduce a new CCG parsing model, which I'm calling supertag factored, in which all the score of a parse is factored on the lexical category decisions. I'm going to show you that with this parsing model, then we can actually do a very fast A-star search for the optimal parse. First of all, a bit of motivation for all this. So there's been some success in semantics recently using CCG in combination with very large unlabeled corpora and using distributional information from these corpora to try and learn something about what the words mean from the logical forms you can get from the CCG parse. If you work with these kinds of approaches, what you find is that the parser is in many ways the bottleneck. They're very data hungry and you need to be able to parse very large corpora, and the parsing takes far more time than any of the training with semantics. And also the parser's performance can be fairly weak out of domain. So if we want to scale up these approaches, we need both faster parsers and better out of domain performance. Right, so CCG parsing is actually really hard. We got a really huge space to search. That's both because we've got a lot of lexical ambiguity and having hundreds of tags for every word, but we've also got a lot of structural ambiguity in that because CCG has a very generalized notion of constituency, then almost all spans can be valid constituents of CCG. And this gives you this huge search space. For a long time, this made people think you couldn't actually CCG parse efficiently at all. But then Clark and Karan introduced adaptive supertagging as a solution to this. Apologies to people in the previous talk, but I'm going to quickly go over adaptive supertagging again. Basically, what you do is for a sentence like fruit flies like bananas, where the words are ambiguous, you first supertag it with a narrow beam, where you output an average 1.3 or something tags per word. You then try doing standard chart parsing with this, and you'll find that with these supertags you can't build a parse. That's because you've got flies having a verb category, and also like gets a verb category. But if you don't get a parse, you just back off, ask the supertagger for more tags per word, and try again. Then you'll get this interpretation is possible, also the other interpretation of the sentence is possible. And you rank these with a complex log linear model. And this involves lots of feature engineering, and it's quite complex to train this thing. So adaptive supertagging does work very well, but I think there's a couple of reasons to be unsure about whether it's really the right solution. The main problem with this is you've got to have some way of setting the supertagger beams that you're going to back off to. And that involves some pretty complex trade-offs. So if you use a wide supertagger beam, what you might expect is that you'll be parsing more slowly, but you'll also be more accurate because the parser's got a bigger space to search through. But actually, what you find is the parser accuracy goes down. The reason for that is that, well, it seems that somehow the supertagger is saving the parser from mistakes it would make otherwise. So it's actually beneficial for parsing accuracy to have narrow beams where possible. On the other hand, if you have a ton of narrow beams, then you'll find that parsing is very slow. So there really isn't a very good principled way of setting these supertagger beams, and you just have to do it empirically on your development data. But even if you get the supertags beams really well on the Wall Street Journal, there's no guarantee that these will generalize well to other domains. So for example, I showed you in the previous talk how the supertagger accuracy gets a lot worse in other domains, and presumably the best supertagger beams will be different in those domains. Okay, so in this talk we're going to try and replace adaptive supertagging with something else. I'm going to introduce a new CCG parsing model, which is supertag factored, and then I'm going to show how with this model you can actually search very efficiently for the correct parse and get for the optimal parse, and find that without doing any beam search at all. Okay, so first of all, supertag factored CCG. In this model, the score of a parse is simply the product of the probability of all the supertags in the parse. In particular, we're going to have absolutely no model at all of the derivation of dependencies. We're just going to have a deterministic grammar. So we're just going to write down something like 8 CCG combinators and a handful of unary rules. And that's going to be our entire grammar up above the lexicon. We still need a parser for this to try and ensure consistency so that we get a CCG derivation we could do semantic interpretation with. Just to show you how this works, so the score of each of the spans in these parts are the scores of these supertags. So we get the scores of these supertags just by running the model I described in the previous talk and using that to get a distribution over tags for every word. So the probability of fruit flies as a noun phrase is 0.4 times 0.3, it's 0.12. The probability of the sentence is 0.4 times 0.3 times 0.9 times 1. So a very simple model. This interpretation obviously uses the scores of these other supertags. Okay, so why are we doing this? Well, firstly, I think there's something inherently good about simple models. It's very easy to implement this kind of thing, and it should be easy to replicate results and to extend it with new features. Also, I think there's a more interesting scientific question here. Like with these strongly lexicalized formalisms like CCG, do we actually really need to model the derivation of dependencies? Which we'll be investigating. And finally, with this model, we can do some very efficient parsing with a nice trick. On the other hand, there's quite a few reasons to be a bit skeptical about whether this model is really a good idea or not. The most obvious one is cases where the supertags aren't sufficient to actually disambiguate the sentence fully. So even given the set of supertags, there are multiple interpretations. One kind of thing, construction where this happens is coordination and scope ambiguities. So these supertags for clever boys and girls, then we can make one interpretation where only the boys are clever, or we can let clever take wide scope with a different parse. Obviously, we don't actually have any model of this, so we're just going to deterministically always go with high attachment in these cases, which I found empirically work better on development data than low attachment. The supertagging model is just what I described in the previous talk, so only using word embeddings features, 2 character suffixes, and capitalization. And that's all features in our parser. Okay, so that's the model. Now I'm going to show you how we can actually parse with this without doing adaptive supertagging. We're going to do this with an A-star search for a derivation. Now, in general, A-star search is a search where you expand your space node by node based on, and you do that in order of the cost to get to this node and an optimistic estimate of how far it is from that node to where you want to go. So this represents an upper bound on getting to the goal via this node. It's important that this, well, in general it's trivial to give these optimistic estimates on the cost to get to the goal, but the closer it is to the real cost, the faster your search will be. So we can easily apply this to parsing by expanding the chart in order of the inside probability of an entry multiplied by an upper bound on the outside probability of an entry. But calculating this upper bound on the outside probability is going to be the tricky bit. So A-star parsing was introduced by Klein and Manning and then applied to CCG by Owley and Lopez. The approach they use for getting this upper bound is to basically sort of hallucinate the best possible outside context for the sentence that gets the best score and use that score. So for example, if we've got this span likes bananas as a verb phrase, what we're going to do to calculate an upper bound for this is to kind of throw away the first 2 words and try and think of the best 2 words start to the sentence that maximizes the chance of getting likes bananas as a verb phrase at the end. So for example, something like hungry monkeys like bananas. This isn't exactly what they do, but it gives the intuition. So there's a couple of problems with this. Firstly, it's quite a coarse estimate of the upper bound and the outside probability because it's not really looking very carefully at what words are actually there. And secondly, doing this hallucinating at runtime is very expensive, so instead they pre-compute all these upper bounds, which results in having huge lookup tables. In our model, life is actually a lot easier. We've got a really good, easy way of estimating an upper bound on the outside probability. To do that, we're simply going to assume that for all the words not in your current span, then you can take the best probability supertag. And because supertagging is actually pretty accurate, then often this bound is going to be very close or exact to the real cost. So we've got this likes bananas as a verb phrase span. The upper bound on the outside probability is going to be the product, the best tags for all the words not in the span. So here, 0.6 times 0.7. Okay, so because that's a monotonic upper bound, this search is guaranteed to work and is guaranteed to find us an optimal solution. It's probably a little bit opaque as to how this parsing actually works though. So I'm just going to spend a few minutes walking through how it parses a sentence, just to try and give you intuition as to what it's doing. So during the parsing, we're going to maintain two data structures. One's going to be the chart, and the other will be an agenda of items we're going to add to the chart. We're going to initialize the agenda from the output of the supertagger. So let's say we get these supertags to our favorite sentence. And first of all, we're going to put all these supertags into our agenda. So items in the agenda are going to be sorted by the cost, which is the product of the inside probability and the upper bound on the outside probability. So for this word fruit as a noun phrase, then the inside probability is clearly 0.6, and the upper bound on the outside probability is 0.7 times 0.9 times 1, which gives this 0.378 score. If we use this lower probability supertag, obviously that's got a lower upper bound. Then if we put flies in as a verb, as an intransitive verb, we'll find that the inside probability is 0.7, the outside probability is less than or equal to 0.6 times 0.9 times 1. And this also gives the same score as the fruit as a noun phrase. And this isn't a coincidence. It's pretty obvious that if you choose the best supertag for any word, then you're not going to, they're all going to have the same upper bound on the probability of the parse. So if we just add all these supertags, we'll get this, where at the top of the agenda, we got the best supertag for every word, and then we got the lower probability supertags lower down in the agenda. Next, we're going to parse with these. So on the left, this is our chart, which is initially empty. And then we're going to do parsing by popping items off the agenda into the chart, and then seeing if there's more items we can add back onto the agenda, if CCG combinators can be applied. So first of all, we pop fruit off from the agenda as a noun phrase, then this tag for flies. At this point, there's a CCG combinator that can apply between these, so we can do backward application on the verb phrase onto the noun phrase to make a sentence fruit flies. For the same reason, because it's only using the best supertags for every word, then the cost will be the same as for the other best spans. That isn't on our chart yet, it's just a hypothetical item. We'll put that onto the agenda. Next, we'll add supertag for like. The next item is this bananas as a noun phrase. Again, we got a CCG combinator we can apply here, and that will, again, this is only using the best supertags for every word, so it's got this 0.378 upper bound. Then we can keep on popping spans off the agenda into the chart. And we get to this point. At this point in the parse, then, what we've done is we've assigned the best supertag to every word, and we've built as much of the chart as we possibly can using these supertags. And at this point, we haven't found the derivation for the whole sentence. So what we're going to do is we're forced to start using lower probability supertags, which lower the upper bound on the whole score for the sentence. So we pop this entry for fruit in as an adjective. We still can't get any further, so we add flies as a noun phrase. At this point, we can apply fruit as an adjective to flies as a noun and get this span for fruit flies as a noun phrase. we'll pop that item back on the agenda. It gets popped straight back off again because it was on top of the agenda. At this point, we can then apply the verb phrase likes bananas to the noun phrase fruit flies. And pop that off the agenda again. And we got a span for the sentence. Now, the magic of A* is that when we find something that spans the sentence, that's guaranteed to be the best possible parse for the sentence under our model. The other magic thing is that we haven't actually had to look at this low probability super tag for like as an adverb. In fact, in general, we're going to get hundreds of super tags for every word from the super tagger, but we only ever need to look at the best, well, at the good ones. So normally we'll have thousands of items on the agenda we never bother looking at because they're not required to make a parse. So this is what lets us search this huge space efficiently without doing the adaptive supertagging or beam search. So just to contrast this approach with adaptive supertagging. In adaptive supertagging, what you do is you add a bunch of tags for every word in a sentence, you try and make a parse. If you don't get one, you add a bunch more tags, and you keep on doing that until you can find a parse. In A*, instead what we can do is incrementally add super tags to the chart. We're going to add just enough until we can guarantee that we got the best parse of the sentence, and then we're done. So let's see how this works. So the blue bars here show the performance of the CNC parser. The red bars is our model. And the yellow bars are the model I introduced in the previous talk using this embeddings-based supertagger combined with the CNC parser. First of all, what you can see is that in domain, our model isn't as good as the other ones. It performs a couple of points worse, though it's not terrible. But the moment you go out of domain, the story changes a bit. So our model is actually a fair bit better than the CNC parser on two different out-of-domain settings, and which I think is quite surprising given that the CNC parser has this huge complex log linear model for ranking parsers using all sorts of features of the dependency and derivations, and it seems like these don't help that much. I mean, even compared to the model I introduced in the previous talk, we're only getting very tiny improvements using all these features as opposed to just using this very simple model where we just take the supertagger outputs. So it seems that all these bilexical dependencies and things, while they are very helpful in domain, they're not generalizing very well at all to other domains. We also looked at the speed of parsing. So the blue here is the time taken for supertagging, and the red is the time taken for parsing. Our simple, most naive implementation actually is about as fast as the CNC parser, which is already a highly optimized, very fast parser. And then by doing some very mild optimization with just doing things like having a tag dictionary and some very mild beam search, we can get something that's very fast, around 4 times faster than the CNC model. We also experimented with seeing how this thing works in downstream applications because we're motivated by semantics here. Basically, we took some state-of-the-art question answering system from Siva Reddy, and we tried swapping out the CNC parser for questions with our parser, and we found that the upper bound increased by around 4 points, so that's encouraging. Okay, so in conclusion, in this talk I've shown that almost all ambiguity in parsing can be reduced to lexical ambiguity. And when you go out of domain, then just having the simple probabilistic lexicon with a little bit of deterministic search on top works basically as well as having a huge complicated model for ranking parsers. And I've also shown that parsing with this is very fast and much more so than using adaptive supertagging. And the parser is available from here. Thank you.
Thank you.
Hi, so I was a little confused.
Yeah.
Earlier in the talk, you said that the super tags don't. There's still ambiguity even given the super tags, but you are working out a derivation with this parser, right? You said something about just choosing high attachment.
Where there's like ambiguity even given the super tags, we just always go with high attachment.
But your A* search is working out a derivation, isn't it?
Sure, yeah, so if it's got a choice where to attach
Oh, okay.
things, it will just prefer the one that goes with. it just throws out the one with low attachment
Oh,
and
I
goes
see.
to the high
Okay.
attachment.
Well, I mean, couldn't you then actually apply a proper parsing model after the fact to?
Yeah, so I mean, that's obviously about the simplest, most stupid thing you could do, and it still works even doing that.
Yeah.
So, yeah, there's a lot of low-hanging fruit in this model, and that would be a very obvious place where I'm sure you can make it a fair bit better.
A couple of questions. Did you try using the CNC Supertagger within your A-star parser?
I did, yes. I didn't show results because basically it sucked. You can't really, the model didn't work at all. I think the Supertagger just wasn't giving the right tag often enough to.
Right. Yeah, because I was going to say it sort of gives you an extrinsic evaluation, I guess, of the quality of the probabilities that the different models are predicting, which is kind of concordant with your earlier presentation.
Yeah,
that in terms of ranking, you're perhaps not seeing the differences, but I suspect your word embedding based super tag is actually getting much better probabilities.
Exactly, yes. So, yeah.
Another question. I mean, there's been some really interesting work on sort of doing analysis of, or sort of a decomposition of parser evaluation over particular constructions using the CNC parser.
Yeah.
Just out of interest, have you tried looking at some of those sort of harder constructions with your much easier parser?
Right, yeah, that's a good question. So I think, I haven't personally, I think Mark did some experiments with this on complicated long-range dependencies using extraction from relative clauses. And I think he found that it worked basically as well.
Yeah.
Possibly slightly worse.
It doesn't work quite as well as the CNC parser because it doesn't have a proper head dependency model.
Right.
CNC gains a lot from that.
Right.
But it's the kind of, if you made a move that was suggested, that made it quite a real question. I think it would be
Yeah.
Yeah.
as a
Yeah.
cool.
Thank you.
Hi, yeah, that's a very interesting couple of talks. I was just wondering if you had any thoughts about how to make this left to right incremental in giving you the best results possible after each word.
Yeah, so I mean, there's no reason you couldn't just do this A-star search in an incremental way where every time you add a word, you just search for a span that will do that, and that should just work. The tricky thing with that is that CCG, at least CCG bank grammar, isn't fully incremental. There are some constructions where you can't analyze in a fully incremental way, so you'd have to do something clever to deal with those.
Okay, thank you.